Symbolic functions. For the function f of x equals minus 5x plus 1, find each of the following. Here my function name is f, and my input variable is x, and my output is given by the formula negative 5x plus 1. So when I'm asked to find f of negative 3, and remember this is read f of negative 3, this tells me that negative 3 is my input. It's in the input location. So I'm going to plug this in for the x variable, which is the input from my function. So I'm going to plug in negative 3 for x using the formula above, which gives me negative 5 times negative 3 plus 1. Simplifying this gives me 15 plus 1, which is 16. So my answer would be 16. And if I wanted to write this as a statement using the function language, I would write this as f of negative 3 is equal to 16. It's another way of saying if my input is negative 3, then my output is 16, where the function is given by this formula. Looking at the next example, f of x plus 3, it's no longer as clear what is meant by this input and what is meant by the output, but we're still going to follow the same basic format and take this whole expression and plug it in for x. So whatever shows up as my input gets plugged in for the input variable, which in this case is x. Since I have a variable expression as my input, I'm likely to end up with a variable expression as my output as well. So I still take the formula negative 5 times, this time the input, x plus 3, minus or plus 1. And this time I have to simplify. I'm going to distribute into those parentheses to get negative 5x minus 15 plus 1, which becomes negative 5x minus 14. So this could be my final answer. Or if I wanted, again, to write this using function language, I could say f of x plus 3 is equal to negative 5x minus 14. Part of getting used to the function language is being able to look at something like this and understand it, and to understand that we're done with this problem. We get so used to solving equations, getting x alone on one side of the equation, moving things away from x, that sometimes there's a temptation to think that you're supposed to do some algebraic manipulation on a statement like this. But for one thing, we can't get x alone here, because remember that this is not multiplication. This is a function name followed by the input x plus 3, and on the other side over here with the negative 5x minus 14, this is telling us that that is what our output is. We are done with this statement. Going on to the next example, we have a minus sign in front of our f of x. We want to remember that the function also operates as a grouping symbol, so I want to find my whole f of x and then apply that minus sign last, which means I'm going to have a minus sign and then some brackets, and I'm going to write the entire expression f of x inside these brackets. And I'm not going to think about that minus sign until I'm done simplifying the inside of these brackets if necessary. In this case, since it's just f of x inside there, there's no extra simplifying that can really be done. So we'll bring in this minus sign using the distributive property, which will change the signs of both terms, and this becomes 5x minus 1, which again could be our final answer. And again, if we wanted to write this in function language, we would say minus f of x is equal to 5x minus 1, and that's all we would say about it. equations and functions. I've mentioned that the default output variable is y. So if we're thinking about this whole y equals f of x or f of x equals y sort of scenario, it is sometimes possible to go back and forth between an equation language and a function language. In this first example, we're told that y is a function of x if y is defined by the formula 2x minus 3. And we could express this as a function just by replacing our y with f of x, so that we could write this in function language as f of x equals 2x minus 3. It's not really doing anything different, but it's written in a different language, and therefore we could then start to use this language on this expression 2x minus 3. It's not, however, possible to just write any old equation as a function. It still has to satisfy the definition of a function. 2x minus 3 is no problem. If I take any value of x and multiply it by 2 and then subtract 3, I'm just going to get a single result. There's no way I can get two different answers just doing those operations. However, if we look at this second example, y equals plus or minus 3x, we can very quickly come up with some examples of inputs that would get mapped to two outputs. For example, if x is equal to 1, then y is equal to positive 3, or y is equal to negative 3. And this is why we would say that this equation does not represent a function. And we can't just go and replace that y with an f of x and call it a function, because it doesn't satisfy the definition. So when we're asked to determine whether an equation shows y as a function of x, we're being asked to figure out whether or not the definition of a function is satisfied. Generally, if the equation is solved for y, or can easily be solved for y without the use of a plus or minus symbol, then we would say that it is a function. So this first example we would say no, the second example we would say yes, and what we're looking for is solved for y without the use of a plus or minus symbol. It might be necessary to solve the equation for y ourselves. If it is possible to solve for y without introducing a plus or minus symbol, then it is a function.